application where we can actually not only try to fit a bunch of data with a parabola, with a quadratic function, but also use a graphing calculator to do all the work for us. Okay? All right, so here's the question. So the table shows the approximate height of a model rocket t seconds after takeoff. Our first mission is to find a quadratic model for the height of the rocket given the time. And then once we have that, let's use the model to estimate the height of the rocket after 1.5 seconds. So here you can see, here we have the table. This is time in seconds and the height that's traveled. Half a second, it's at 23.5 feet. At 1 second, it's at 38 feet. So you can see it's still going up. At 2 seconds, it's at 40 feet, so it's really high. At 2.5 seconds, it's at 27.5 feet. So now it's beginning to drop already. Well, it's not beginning to drop, it's already dropping. And then at 3 seconds, it's 9 feet off the ground. How do we do that? Well, we take our graphing calculator, and we're going to, first of all, input this table into the graphing calculator. Okay, and I'm going to do all this stuff here because it's a little bit small here to see it, so I'm going to do it all here. So we're going to do what's called quadratic regression. Okay? So we hit the Stat button, and then we go to Calc, and then we press option 5, go down to 5, and hit Enter. Okay, now once we do that, it's going to spit out an A, B, and a C. Those are going to be the coefficients. The A is the coefficient on the x squared term, the B is the coefficient on the x term, and the C is the constant coefficient in our quadratic. And here you can see what it looks like after the quadratic regression. So check it out. And you can see there are the values for A, B, and C for this particular data set. See how quickly it does it? It's pretty neat, isn't it? That's pretty cool. Okay, and so what you can do now is you can use a table to find H when t equals, well, first of all, let's calm down. So first of all, let's enter the equation in the graphing calculator. So we're going to now enter that in with those values. And so you can see I'm entering it in. So it's y equals, get the y equals t, and then input all that. And now we can use a table function, which I'm going to do right now live. So there's a table function to use to find the height, h, when t equals 1.5, and you can see right here, if you look, you see it says 1.5, and you can read off what the y value is, and you can see, okay, you can see it, I can't see it because it's facing you, but I'll turn it now, that it's 42.818 feet. And so, in fact, the question says, find the height of the rocket at 1.5 seconds, and we see it's 42.818 feet. Is that consistent? Well, 1.5 seconds is between 1 and 2 seconds, and so here it's 38, and then here apparently it's 42.8, so it's still going up there, and then by 2 seconds it's already down to 40, and you can see that we're already dropping ground. So this idea of using quadratic regression on a graphing calculator is a really neat way to take a bunch of data and extrapolate the values in between. Terrific. Have fun thinking about modeling with quadratics. You know, often when we have data and we see it has a down and an up or an up and a down, we might want to see if we can model it by a quadratic or the curve, the parabola. Let's take a look at an example where we can actually see different types of parabolic representations or models for a collection of data actually give slightly different outcomes. Let's have a look. The yearly average high temperature in Brooksville is 65 degrees Fahrenheit. Now, the ordered pairs M, D give the month of the year M, where January is month 1, and the number of degrees D, Fahrenheit, by which the average high temperature for the months May through October exceeds the yearly average high. Now, a vertex model of the data is given by this blue equation and the blue curve, and a regression model in the green is given by the green curve. The blue vertex model actually I found in a previous lecture, and the green regression one requires either a graphing calculator or you could use calculus, which we don't quite know yet. But either way, you can see that both reasonably model the data. In fact, maybe the green's a little better since it's a little more sophisticated, but you can see they're pretty close, but not identical. Anyway, given all of this, let's see if we can apply this to something of interest. So, Danny is moving to Brooksville from Longwood. Now, in Longwood, the greatest monthly average high temperature is 89 degrees Fahrenheit. And there is a 120-day period where the average high temperature is at least 80 degrees. So, a couple questions here. Here's the first challenge. Let's graph the line D equals 24 on our grid, and then figure out what that line represents. And then I want us to wonder what conclusions might Danny reach using the graphs of the two models to compare Brooksville and Longwood. Okay, so the first challenge is to look at the line D equals 24. And so D equals 24, that's way up here. I'm going to actually have a line right here. Line available, D equals 24. Oh, and there it is. So when you look at that line, what does that represent? Well, remember, that's 24 degrees is the change from the average, and so what that represents is the temperature, because remember the average is 65, so 65 plus 24, it equals 89 degrees Fahrenheit. And when you look at the two curves, what do you see? Well, you see that the blue curve seems to go over it for a little bit, almost for about a length of a month, where it's a little bit higher, and then comes down, and then the green curve goes up and just nicks it right there, just touches it, and then comes down. So, there's a lot of things we can conclude here. I've written them all down for us. So here's what I might conclude. So from the Vertex model, that's the green one, we could conclude that the greatest monthly high temperature in Brooksville is a little higher than the greatest monthly temperature in Longwood. And you can see that because it's above the 89, which was the high in Longwood. And there's about a 1 month period where the average high temperature in Brooksville is greater than the average high temperature in Longwood. Now, if we use the regression, the green one, we see that the greatest monthly high temperatures in Brooksville and Longwood are about the same, because it just comes up and grazes, just kind of tangent to it, we say in the business. So basically, that's what we conclude here. Neat. Now, here's a follow-up question. Let's graph the line D equals 15 on the grid and figure out what that line represents, and then compare the predictions of the models for how long the period is in Brooksville with an average high of at least 80 degrees, and how does that compare with Longwood? So, first let's look at the line D equals 15, which we go right across here. I hope you can see this. This is going to be a little tricky. And again, we're estimating here. Okay, so let's take a look. So first of all, what does that represent? Well, we have to take 15 and add it to 65, and so that line, D equals 15, represents a temperature of 80 degrees, which is exactly that temperature that we were given as the point of consideration. So where do we see that the temperature is greater than 80 degrees? Well, if we look at the Vertex model, remember that's the blue one, we see that it starts over here, and then it's higher, 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 and it goes till about here. So look at the interval from here to here. Notice that the blue model actually has a shorter time span where it's above, whereas the green model starts way over here and is always up, and ends way over here. So it's a longer interval. This green the interval from here to here, the green endpoints, is actually longer than the blue interval from here to here. So we see that with the Vertex model, we're going to see that we have a shorter amount of time where the average high temperature is greater than 80 degrees compared to the regression model. And we can actually figure out exactly what that would look like, because, in fact, if we notice here, with the green, let's start with the Vertex model, let's start with the blue, in fact. So how long is that? I'll put my finger there, and I put that here. Well, that's 1 month, 2 months, 3 months. So we all have 3 months. What's the extra stuff? Well, this looks like about a third, and that kind of looks like another third. So maybe it's like 3 months and 2/3 of a month. So 3 and 2/3 of a month, the temperature is 80 degrees or higher. So that's what? That's about 100 days, or 110 days, actually. So we see that 110 days is predicted
by the blue model that we would have temperatures of greater than 80 degrees. And what about with the green model? Well, that seems to be kind of right in between those 2 months. And here that green is kind of right in between. So we have 1, 2, 3, and a half is 4. That would be 120 days. 120 days. So what do we conclude? Well, all said and done, we see that the vertex model shows that a shorter amount of time when we have a high temperature that is greater than 80 degrees compared to the regression model. And that's because the blue interval endpoints is actually a little bit shorter than the green interval endpoints. And the vertex model predicts slightly fewer days with an average high of at least 80 degrees period than Longwood. Because remember, Longwood had 120 days, and here we're predicting about 110 days. While the regression model predicts essentially the same number of days, because we see about 3 months span, which is 120 days. So roughly, they're comparable number of days that the temperatures are over 80 degrees Fahrenheit in both of these cities. Interesting to see how we can actually use different types of models to actually study data. And if the models are decent, the results, the conclusion, should be about the same. And we saw that in this example in terms of temperatures. Even though we have 2 different models, found 2 different ways, since they're both reasonably good, and we can see that through the graphs themselves, they seem to conform to the data, it's not surprising that we're getting similar answers, although not exact. That's the joy of modeling. We're not going to always get it right, but we're going to understand the structure. Have fun understanding the structure in your life. I'll see you soon.